Hello, today I want to show you the application of the wye-delta and delta-wye transformation. Typical applications are unbalanced bridge circuits like this, or very complex circuits like this cube circuit here, where you don't find real parallel or serial resistor circuits. To simplify it with the common known rules. How to solve such problems we will see after the intro. This video is based on video 009EN Network Analysis Part 4, where you see how to simplify parallel and serial resistors, and on video 019EN Network Analysis Part 6, where we derive the formulas for the wye-delta and delta-wye conversion. Today we will do 3 exercises. First, calculate an unbalanced bridge circuit, where we determine the total resistance of the circuit, the voltages and the currents. Second, calculate the diagonal resistance of a cube with unequal edge resistances. And third, calculate the diagonal resistance of a cube circuit with equal edge resistances. And we will here use the simplified solution with the equipotential surfaces. In exercise 1, we should determine the resistance between A and B of these 5 resistors, the voltages U4 and U5, and the current I0, I1, I2 and I3. Due to the fact that the ratio between R1 and R4 and the ratio between R2 and R5 are different, there flows a current through R3. And therefore we cannot use the normal formulas for parallel or serial resistances to simplify the circuit. Here we can use the delta-wye transformation. We see that these 3 resistors build a delta connection, and with our formulas from the last video we can transfer it in a Y connection, and then we have here 2 real serial connection. The 2 real serial connection are true parallel connection, and again the top resistor to the 4 lower one is a real serial connection. Here we have the nodes 1, 2 and 3 of the delta connection, and here the nodes 1, 2 and 3 of the equivalent Y connection. Now we calculate from the resistors R1, R2 and R3 from the delta connection the new resistors R6, 7 and 8 of the Y connection. To transfer the delta resistors into the Y resistors, we use these 3 formulas for R6, R7 and R8. When we put concrete numbers in these formulas, we will get for R6 8.18 kilo ohm, for R7 2.73 kilo ohm, and for R8 5.45 kilo ohm. Here now our electrical equivalent circuit with the new Y resistors R6, R7 and R8 and the resistors R4 and R5 from the original circuit. Now we have to calculate the total resistance of R4 and R7, the total resistance of R8 and R5, then the total resistance of this parallel circuit, and finally the total resistance of the complete circuit. The total resistance of the serial connection R4 and R7 is 32.73 kilo ohm. The total resistance of the serial connection R5 and R8 is 20.45 kilo ohm. The total resistance of this parallel circuit is 12.59 kilo ohm, and the total resistance of all 5 resistors from A to B is 20.77 kilo ohm. Now we calculate the current I0, the voltage U6, the current I4 and the current I5. The current I0 is the voltage U0 divided by the total resistance. The voltage U6 is the current I0 multiplied with the resistance R6. The current I4 is the voltage U0 minus the voltage U6 divided by R4 and R7. The current I5 is the voltage U0 minus U6 divided by R5 and R8. With concrete numbers we will get I0 is 0.578 milliamp, U6 is 4.73 volt, I4 is 0.222 milliamp, I5 is 0.356 milliamp. Now we can calculate U4 and U5. U4 is I4 times R4, U5 is I5 times R5. With concrete numbers we will get U4 is 6.66 volt and U5 is 5.34 volt. Finally we can calculate I3, I1 and I2. I3 is U4 minus U5 divided by R3. I1 is I3 plus I4 and I2 is I5 minus I3. With concrete numbers, I3 is 0.132 milliamp, I1 is 0.354 milliamp and I2 is 0.224 milliamp. Due to the fact that the circuit is diagonal symmetric, we have here and here 30 kilo ohm and here 15 kilo ohm. The current I1 must be equal to current I5 and the current I2 must be equal to current I4. And we see I1 is equal to I5. The small difference is caused by the rounding error. And I2 is equal to I4, and here also the small difference is caused by the rounding error. This is a proof that our calculation is correct. Exercise 2 is a real complex task. We want to calculate the diagonal resistance from A to B of this cubic circuit where all the resistance values from R1 to R12 are different. We can solve the problem by applying the wye-delta and delta-wye transformation several times to this circuit. In the first step, we number all the nodes from 1 to 8 of this cubic circuit and redraw it as a plane circuit. From node 1 we have a resistor to node 2, to node 4 and to node 5. From node 1 we have a resistor to node 2, to node 4 and to node 5. From node 7 we have a resistor to node 3, to node 6 and to node 8. From node 7 we have a resistor to node 3, to node 6 and to node 8. From node 2 we have a resistor to node 3 and to node 6. From 2 we have a resistor to node 3 and to node 6. From node 4 we have a resistor to node 3 and to node 8. From node 4 we have a resistor to node 3 and to node 8. And from node 5 we have a resistor to node 6 and to node 8. And from node 5 a resistor to node 6 and to node 8. So the two circuits are equal. In the next step we number the resistors from R1 to R12 and transfer all the references to the cubic circuit. Now we have to do the most difficult part. We have to apply several times the delta-wye and wye-delta transformation to this network to get real serial connections or real parallel connections of the resistors, which we can simplify with the known rules. And in the end we should have a single resistor between A and B. The way I will show you is maybe not the optimal way, it's simply the way I found in a short time to solve the problem. After you have understood how it works, you can look for another way and maybe you find a way with less transformations. In the first step we will transfer the Y resistors R2, R6 and R7, which are on the node 1, 3 and 8 to the new delta resistors R13, R14 and R15. With these three formulas we can calculate R13, R14 and R15. Now we will move the two green resistors R13 and R14 from the middle to the border of the circuit, and have a look on the nodes 3, 7 and 8, where we have the delta resistors R10, R12 and R15. These delta resistors will be transferred in the new Y resistors R16, R17 and R18. Here's the formulas to calculate the new resistors R16, R17 and R18. Now we will look on node 1, 2 and 3 and transfer the delta resistors R1, R4 and R13 to the new Y resistors R19, R20 and R21. And at node 1, 5 and 8 we will transfer the delta resistor R3, R9 and R14 to the Y resistors R22, R23 and R24. For the nodes 1, 2 and 3 we have these three formulas to calculate R19, R20 and R21. For the nodes 1, 5 and 8 we have these formulas to calculate R22, R23 and R24. Now we have two serial connections, so we will combine R16 and R19 to the new resistor R25, R5 and R20 to the new resistor R26, R8 and R22 to the new resistor R27, and R17 and R23 to the new resistor R28. Here's the formulas to calculate R25, R26, R27 and R28. Now we will transfer the Y connection R21, R25, R26 into the delta connection R29, R30 and R31, and the Y connection R24, R27, R28 into the delta connection R32, R33 and R34. Here's the formulas to calculate R29, R30 and R31. And here's the formulas to calculate R32, R33 and R34. Now we can see R30 and R32 build a parallel circuit. The resistors R31 and R34 are also a parallel circuit. Here we have the link. And the resistors R29 and R33 are also a parallel circuit over this link. So we can combine these parallel resistors to the new resistors R35, R36 and R37. Here's the formulas for calculating R35, R36 and R37. Now we transfer the delta resistors R35, R36 and R37 to the Y resistors R38, R39 and R40. Here's the formulas to calculate R38, R39 and R40. Now we have a simple circuit where we can apply our standard rules for parallel and serial connections. The serial resistor R11 and R38 will be combined to R41. The serial resistors R18 and R39 will be combined to the resistor R42. The two parallel resistors R41 and R42 will be combined to R43. The serial connection of R40 and R43 will be combined to R44. R44 is now our final resistor between A at node 1 and B at node 7. And here are final formulas to calculate R41, R42, R43 and R44. With the spreadsheet I calculate all the resistors until R44 and put R44 also here in this top cell rounded to 1 decimal digit. Now I zoom in a little bit to get a better view on the values. The resistance of the resistors R1 to R12 is set to 10,000 ohm, and we get a diagonal resistance between A and B of 8,330 ohm. This is the correct value, which we will see also in exercise 3 later. To prove that the formulas work even with different values, I will set all the resistances to a very high value and some dedicated resistances to a low value where we know the result to ensure that the formulas work in the right way. I put now all the resistances to 10 gig ohm. And when we now set R1, R5 and R11 to 1 ohm, then we have a diagonal resistance of 3 ohm. I set here 1 ohm, R5 to 1 ohm and R11 to 1 ohm. And we have a diagonal resistance of 3 ohms. That looks fine. When we add now this path here, with R3 1 ohm and R8 1 ohm, then we have here 2 ohm and in parallel 2 ohm here, then 2 ohm and 2 ohm in parallel is 1 ohm, plus this serial 1 ohm we should have 2 ohm. So I add now for R3 1 ohm and for R8 1 ohm, and we see we have 2 ohms, so the calculation works as expected. In exercise 3, we look on the case where all edge resistors have the same value. As we have done in exercise 2, we add the nodes 1 to 8 in our circuit and draw the plane circuit of it. We have here a special symmetry. We have 3 resistors, and each of the resistors is connected to further 2 resistors here and here, and this one here and here. And on the bottom we have also 3 resistors, and each of them is connected to 2 further resistors here and here. And due to the fact that all resistance values are equal, the current through these 3 resistors must be the same. And the same current with the same resistance gives the same voltage drop. So all the nodes here must have the same voltage, and all the nodes here on the top must have the same voltage. Areas with the same voltage like here or like here are called equipotential surfaces. At equipotential surfaces we can do a shortage without changing the electrical behavior of the circuit. Now we can see that we have here 3 resistors in parallel, here 6 resistors in parallel, and here 3 resistors in parallel. And now it's easy. Here we have R divided by 3, R divided by 6, and R divided by 3. So we get R total is R divided by 3 plus R divided by 6 plus R divided by 3. We bring all on the same fraction line and get R total is 5 divided by 6 times R. If R is 10K, then R total is 8,330 ohm. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. See you in the next video. Bye bye.